like a repeater where signals will go from this ship to the satellite, it will receive it, and then it will send it back here. So satellite's role here is like a repeater, and here it is direct communication between a ship and another ship, right? So how will I model this? So for example, how will I design a communication system with these aspects like PT, PL, PR, antenna gain, so that I have reliable communication, right? That is dependent on this formula. So for example, on the ship, you will have a transmitter, and then there is what is called as a free space loss, which is typically in dB, and then you have a GR, and then you have a PR, right? So there is a PT, GT, free space path loss, PL, GR, and PR, mapping to the 5 terms which we saw here, right? So the idea being here is that both a transmitter and a receiver will be present in both the ships. This ship will have a transmitter and a receiver. This ship will also have a transmitter and receiver. So when this ship behaves like a transmitter, it will be PT, GT, free space path loss, GR, PR on this side. And similarly, when this works as a transmitter, the other side, there will be a PT, GT, free space path loss, GR, PR, and receiver. So this is a typical practical example for a ship communication, right? So I hope you understand the bigger context. See, whenever you relate what you're trying to understand with respect to a real-time scenario, right, on how communication happens, it sorts of, you're able to relate with what is being told, right? Meaning these areas are typically heavy on math and there are a lot of equations. But when you start looking at it from an applications point of view, right, things are much more easier. And that is actually what I'm trying to motivate here, where I'm trying to give a practical example and then showing what happens in a typical free space condition with all these variables put in, right? So with this, if you see, the equation is nothing else but PR is going to be PT plus GT minus PL plus GR is going to be the received power, right? So a very, very starting point, a basic equation in RF is this equation, where the received power being a function of the transmit power, the gain at the transmit, the path loss, and the gain at the receiver, right? So with this, you can sort of reach from ship A to ship B, or from ship B to ship A. Both are possible, right? So any questions in this? Feel free to stop me at any point in time. Okay, I'm assuming I'm looking at the meeting chat, so I would okay. So Madam Murugeshwari just pointed out nothing is needed. Thank you, Madam. So we'll just continue. Okay. So getting back, okay. So I think with this background, we'll get into the simulation mode. Okay, with this where we'll be running the first Python code, and we will be doing this. So I would request all of you to look at the following file, the power units 1.py. I'll be opening that. So it's a pretty simple implementation where This is hardly a 10-line Python code where I'm trying to understand what's the what connection between the linear scale and the log scale, right? So typically a power which is mentioned in milliwatts will get translated into a power in dBm using this formula called 10 log 10 of transfer power in milliwatts, right? So that is what is this code talking about. And then let us assume you have a loss of 20 dB and you have a transmit antenna gain of 5 and a receive antenna gain of 5. So I've just implemented the equation which we just now saw, where you do a transmit power dBm plus transmit antenna gain minus loss plus receive antenna gain. And for the sake of completeness, I've converted the receiver power into milliwatts, where I've taken the dBm which is in log scale and converted to linear scale, and I'm printing both of them. Right, a pretty simple code. But see, a majority of the work that happens in the industry needs to have a good understanding of programming, right? Unless and until you're pretty good in programming, right? It is because there are so many scripts and code already available, right? When you're talking about the industry, one is theoretical aspect understanding, and the second very important aspect is programming. How well are you able to code? How well are you able to understand a large code base? And how well are you able to modify codes? See, modification of the code is a very important skill. And because no one is asking you to reinvent the wheel, all the codes are there. You need to come up and take a code base which is already there, modify the code and build a new application, right? Nobody is actually writing an application from scratch today. All applications have already reached a certain stage. I use that as a starting point, modify certain parts of the code, delete certain parts of the code, and I build on top of it. So that's why I'm taking a programmatic approach to this workshop, right? Because I'll be modifying this file, I'll be trying to edit it, and we'll show you how primarily things are worked out and tried. Okay, so let us run this code. I'm just going to use Python power units.py, and I get a simple result here. I hope everybody is able to see this. Transmit power in dBm is 20 dBm, receive power in dBm is 10 dBm, and Rx power in milliwatt is 10 milliwatts, because I've converted the log scale to a linear scale and I'm printing it as 10 milliwatts, right? Where I've done an inverse. So when you go from linear to log version using 10 log power in milliwatts, the reverse will involve taking an anti-log, and that's what I've done here. Okay, so that is this code. So for example, we did a quick code analysis. We now know what the code does, right? So with this, I want to give you a requirement, right? So typically, code modifications, code alterations comes in the form of requirements. Okay, so the customer says, you have the code base now, I have a new requirement. Can you run the same simulation for me at transmit power of 50 milliwatt, loss is 23 dB, transmit antenna gain is 2 dBA and 3 dBA. So there are no changes in the transmit antenna and receive antenna, but he wants us to run the code at 50 milliwatts for the transmit power of 50 milliwatts and a loss of 23 dB. So where should I change it now? What lines of the code should I change? Can people point out to me what lines of the code needs to be changed? Line number? For this given requirement, okay, the requirement being transmit power is 50 milliwatts and loss is 23 dB. These two are programmed here. Transmit power, it's going to be here, right? So I'm going to change 100 milliwatts to 50 milliwatts, okay, and I'm going to change loss to 23 dB. Right? This is a requirement from the customer, right? He has given me a requirement saying change the code from a transmit power of 100 milliwatts to 50 milliwatts and a loss from 20 to 23. And there is no alteration in the transmit antenna gain and receive antenna gain. Okay. So I have now made the changes. Okay. And like I need to now test it. Right. So I know that it's going to be around 50 plus 23, 73. 50 plus 1060 minus 23. So it should roughly come to around 37, right? I'm expecting the answer to be 37. Let us see what happens. So I hope people have got what's happening here. We are just changing the parameters based on the requirement. So the receive power is 4 dBm. So 50 transmit power in dBm. Okay. Yeah. Yeah, I hope people got it. I did not convert 50 to dBm, and hence I made a mistake in the initial calculation. But your receive power is 4 dBm now, which translates to 2.5 milliwatts. Right? This is the result of the new simulation. Right? So what did I do was change the code, alter the linear power, which is 100 milliwatts to 50 milliwatts, converted into the log scale, and did the loss calculation, meaning updated the loss variable, and found the receiver power also. Okay, so that is typically what is a requirement, right? Now let us look at the next requirement. The next requirement says it is going to be transmit power of minus 15 dBm, loss is 10 in linear scale. Okay, and the transmit antenna again and the receive antenna again happens to be the same, right, as the previous thing. So what is the change that I should do now? Now that the requirement has come in the linear scale, I should basically convert the loss from linear scale to log scale, right? So I'll basically have to do a 10 log 10 of 10, which is basically 10, and the transmit power is minus 15 dBm, right? So for requirement 2, what I will do is I'm going to go, since it is directly given in, I'm going to comment this. I'll put here as minus 15, right? And I have a loss which is 10. Okay, in dB. So I'll code it as loss in linear equal to 10, and then I'll put loss in dB equal to right. And I'm going to run it. Right. So basically, for this simulation, you have a transmit power of minus 15 dBm, receive power is minus 15 dBm, and your receiver power in milliwatts. Wait a minute. It is, what is the issue here? Can somebody point out? right? So what should be the change? Which line should be changed? Where is the mistake? Any suggestions? Anybody wants to try? See, this is a typical example, right, of how we debug, right? For example, there could be floating point issues, fixed point issues. That is why I brought up this, okay? Because when you try to do something and then you try to figure out what is the issue, you learn much more than just looking at a model, right? So I would request somebody to give a suggestion on what I should change in the code so that this will actually start working. Is there a problem in the log to linear conversion, or or is there a problem in the precision? Any suggestions welcome. We'll change the code and see.
So we have the suggestions from in the chat box also, sir. Dr. S. Murugeshwari has suggested something.
Okay, I think we'll proceed. I would request someone to provide me the inputs, meaning on analyzing it. It's a pretty obvious mistake, okay? But if it can be analyzed as whether it's a floating point issue to fixed point issue, or has it got to do something with the local linear conversion, and then sorry, I think so. The loss in linear, yeah. So what should be changed? I think uh, Pooja madam is saying that loss is in linear. So what should be changed? Okay. Exactly. I think that's precisely the point here. So, especially when doing such calculations, right? The precision is of a big issue. I think rightly pointed out because of the value, and we need to alter the code to make it work, right? So, when a requirement is given, right, you'll have to consider all forms of typical variations. That's why I actually gave a variation where one was it is as it is, right? You have the code already in transmit power in milliwatt, and then the loss is in 23 dB. And now I wantedly change the loss to 10, okay, and also reduce the transmit power, right? And I reduced it really hard. You can see I moved it to minus 15 dBm. Okay, so it is important that you develop the code and test the code for different combinations, because then only your precision issues will come out, right? When you have a better handle of precision issues, you know how your code will perform on the field, right? So many times you get a lot of field issues because of lack of handling the precision issues and not testing it adequately, right? So it is important to write a lot of test cases and test it for various combinations before you ship your code. What you typically do as shipping your code, before that you should do a lot of testing for corner cases, and that is what we hit today, where because I reduced the transmit power and I also did some calculations, we have hit a corner case, right? So I hope people got the point. The point here was to bring out the importance of precision, right? And you can modify the code, alter the precision, and come up with your own simulations. So please remember that, especially when you're doing SNR-BR calculations, these precisions, floating point, fixed point are extremely important. Okay, and these could mean a couple of dBs, which is a huge thing in a wireless link budget analysis. So be extremely careful about precision, right? Excellent. I think that was a very good answer, where we understand that the importance of precision. Okay, fine. So let's go forward. Any further questions? Okay, I find there are no questions right now. Okay. So let's go forward. The next one is going to be, I'm going to talk primarily about free space path loss, okay, where the idea is you have line of sight based computation, where it is used to predict the strength of a RF signal at a particular distance. See, when we are talking, right, and there is a person A and person B, or a transmitter and a receiver, the distance between them, as it starts increasing, right, obviously the signal will be heard lesser on the receiver end, because of a fundamental property of the air, which is called attenuation, right? So because your signal starts attenuating, you have your signal strength reducing, and beyond a point, even though you're talking, the person who is listening to you never listens to what you're saying, because you're not hearable. What is called the distance is so great and the attenuation is so great that the signal fades away, right? So how do you categorize this? This categorization is what is called as path loss, and there are different models for it. Today, we are going to look at a very basic path loss model called free space path loss, and we'll be looking at how to model it. Okay, but please remember that any model is ultimately a model, in the sense these are theoretical values, right? And in the real world, a typical scenario will have so many other things like obstacles, reflections, losses, which needs to be accounted when estimating the signal at a location. Okay, so FSPL is a good starting point to analyze what is meant by path loss. Okay, but real world path loss model will have to take into consideration a lot more other things, right? We'll have to take into consideration a lot more other things, because there are a lot more other obstacles, and based on that, your received signal will differ. Okay, so once again, your free space path loss will be taking into consideration the above equations, and the gain offsets by a certain decibel value. But primarily here, we will be looking at the effect of distance and frequency on the path loss. This free space path loss model will primarily look at the effect of distance and frequency. Okay, and it is important to understand that when you talk about free space, that we are assuming that the RF signals are going to be propagating in air. If they are propagating in any other medium, right, this model will not give you the right result, right? So it is important that to understand free space path loss is for a medium like air, and for other mediums it doesn't work. For example, like you have fiber optic based mediums, or you have vacuum or whatnot, which are other mediums. This model doesn't work. Then the dependence on distance and frequency, which we are right now going to see, is applicable only for free space path loss. Okay, fine. So with that, let's move on. So we come to the second simulation. Okay, so what I'm now going to do is I'm going to once again go through the code, which is FSPL simu2.py. I'll run it once, interpret the output, and then study the code, and I'm going to do modifications. Once again, this is like you getting requirements from the customer, and you're expected to do this analysis and send a report, right? So there are 3 requirements, and I'm going to model the code based on these 3 requirements and study the output and send a report, right? That is going to be the typical work pattern, right? So let me open up FSPL simu. Okay. So here, once again, let us quickly go through the code. I've got a very simple code where D here stands for the distance. It is going right here from 40 meters to 7 kilometers. I have an array, and once again, I also have it for frequencies starting from 1900 megahertz right up till 60,000 megahertz. What is 60,000 megahertz? What is another way of saying that? You can say it as 60 gigahertz, right? So basically, you have a frequency array which is going from 1900 megahertz right up till 60 gigahertz or 60,000 megahertz. And for the sake of dimensionality, I've just kept it all in megahertz. And it is useful to see that 1900 megahertz stands for GSM, 2100 for WCDMA, 2400 for WLAN, 2500 for LTE, and then a couple of more WLAN bands. And then you have satellite bands and WLAN, right? So here we are looking at different technologies, starting from GSM, which is 2G, WCDMA, which is 3G, then you have LTE, which is 4G, and then you have satellite. And of course, you have your 802.11 standards in the form of WLAN. So 1, 2, 3, 4, 5, 6. I have around 9 frequencies and about around 10 distances. Okay, I'm going to do an analysis on how the free space path loss changes by changing these distances and what frequencies. Okay, so what I'm going to do is first initialize. See, initialization is a very, very important part of coding. So it is important that you initialize, right? And then using the free space model, I'm going to just capture the effect of frequency here and the effect of distance here. Okay, and then this is the whole net equation, okay, where it's going to be log fc plus log d and constant, and I'm going to plot it here. Okay, I have 2 plots. So one is going to be the path loss in dB due to distance from transmitter, and then frequency in megahertz used in TX, and then the path loss. So basically, the objective of this is to see the amount of path loss because of distance and because of frequency, right? So let us just, I hope the code, what we just now did is called the code walkthrough, okay? Where we look at the code, we look at where the initialization is happening, where the computation is happening, where the plotting is happening, and we know the sections of the code. See, for example, this is the part where things are getting initialized, and then this is a comment which tells about the different frequencies in which this operate, okay? And then this is the initialization for the buffers. Buffer initialization happens here, and then the actual computation happens here, and then you have the plotting, right? So these are typical parts of the code, right? One is the initialization, then the computation, and then the plotting. So that is what is shown here. I'm sorry. Someone saying something? Okay. So going forward, would run it, and I get this plot. So what does this plot now talk about? This plot basically says that as I move away from the transmitter, right? See, this is 40 meters. This is 80 meters. Just look at the 40, 160, 320, 640, 1.28 kilometers, 2.56, 4 kilometers, 5 kilometers, like that. When I'm moving from away from the transmitter, I find that my path loss is increasing, right? So at around 6 kilometers, I have close to around 48 dB path loss, right? And at around 7, it is meaning not 48, it is, yeah, meaning 48, 49, like that, I'm getting path loss. And when I'm talking about, say, something like 2.5 kilometers, I'm at around 40, right? So when I'm around 1.28 kilometers, I'm at around 35 dB. And then when I'm around, say, 800 meters, I'm at around 28 dB. So now this is a good plot, right? Which tells me how your free space path loss maps to distance, right? So obviously, greater the distance, greater is the loss, which means lesser the receipt power. Okay, so this confirms our assumption that when the transmitter and receiver are getting separated, you're going to have bigger losses, right? So that is what this plot confirms. And the next plot, this is the plot with respect to frequency, right? So you have on the x-axis in megahertz, you have 10,000 megahertz, 20,000 megahertz, like that, and the y-axis is your path loss, right? So you can once again see that with increase in frequency, you're getting a higher path loss, right? So so one open question to people: let us assume you're trying to build a communication system where you want to have minimum path loss. Which is the end of the spectrum that you will prefer? What will be your center frequency? Will it be say closer to what? So will it be like 900 megahertz or 60 gigahertz? Which center frequency will you choose if you want to have a lower path loss? Obviously, something like 900 megahertz, right? Because the path loss is lesser, and you would want to go with 900 megahertz for your design, right? Because you have much less path loss. On the other hand, the advantage of going for a higher frequency like 60 gigahertz is that you have large amounts of unused bandwidths there. So if you're able to come up with an RF system and antenna based design where you can reliably communicate there, of course at very, very short distances, then you have a large amount of bandwidth available there. Okay, and that is what is typically now referred as your millimeter wave communication, which is happening at 60 gigahertz, 28 gigahertz at different standards, right? So that is why I've plotted both, starting from like 900 megahertz, which is used in your 2G system, right up till 60 gigahertz, which is used in your 1180 platforms. And roughly somewhere here comes your 5G, right? Around 28 to 30 gigahertz is where your 5G millimeter wave systems are being envisioned. So you will now get a certain idea about the effect of path loss versus frequency and path loss versus distance. And in general, higher the distance, higher the frequency, more the path loss. Lesser the distance, lesser the frequency, lesser the path loss, right? So it is what inversely related, right? That is the point which comes out here. Any questions on this? Meaning, I hope this is one of the basic concepts, so everybody is clear with that. Any questions? Feel free. Yeah. So that's great, right? I find a lot of answers coming in. That's awesome. So how can the more bandwidth or available option? Mr. Karthikeyan says, how can be modified? Can you be more specific? What do you mean by modified? Mr. Karthikeyan?
So, Mr. Karthikeyan, if you want, you can unmute and speak.
Sir?
Yeah.
Sir, if I'm basically designing a HFS antenna designing,
Okay.
in the written laws, how can I modify it?
Modify what?
Modify the antenna based I in my antenna.
No, actually, your signal is breaking, Karthikeyan.
Sir, is I am audible?
Hello. Yeah, please.
Sir, in antenna, which part can be modified to get more number of channels or to increase the bandwidth?
Oh, okay. So see, when we're talking about bandwidth here, right? I'm talking about the overall system design. So, for example, when you talk about you have your LTE systems, right, which work at 20 megahertz. So you could potentially configure it 20 megahertz or 40 megahertz or the baseband bandwidth and passband bandwidth, right? So I'm referring to that. If you are asking me about antenna design and how you can increase bandwidth in that, I am not an expert in antenna design. My point where I'm talking about bandwidth is primarily with respect to the baseband bandwidth and passband bandwidth and how you can use it. Whereas there, I have certain understanding on how you can work on directional antennas and how you can work on omnidirectional antennas. For example, the beamforming nature which comes up from the phi layer, right, is some areas which I worked on, right? So maybe when you're talking about how to increase antenna bandwidth, if you can ask me about in which product and share some data sheets, right, I can take a look at it and share my opinion about it. Does it answer your question, Karthikeyan? Sure.
Yes, sir. Thanks, sir.
Okay, so let's move ahead. So once again, I would request people to maybe try this. So I'm going to quickly add the code for modeling a distance of 8 kilometers, 40 gigahertz, and look at it. Okay, so I'm going to look at requirement 1 and requirement 2, where I'm going to go back to the code. I'm going to add one more parameter here, comma 8.0, and I'm going to add 40 gigahertz. Right, so save it, and I'm going to run it. So right now I've got 8 kilometers as well. At 8 kilometers, I'm just crossing 50 dB, right? So I've got the new point here, and I've also got it at 40 gigahertz, okay, which is somewhere between 92 and 93 dB path loss, right? So the requirement came up, okay, and see, the important part here is to figure out, okay, this is a D array, okay, and I'll insert a value here, right? And this is a frequency array, I need to insert a value here, right? So only when you understand the whole code base, right, then you know where to go and insert, right? That is why it is so important to understand what is the existing code base, what are the plots it is giving me already, and how should I modify it so that I get the required results. And see, for example, this is once again how a typical requirement from the customer would look like, right? So he says, okay, fine, I need to do a study I agree that your model works till 7 kilometers. Can you extend it for 8 kilometers and give me a suitable plot? Okay. And I'm planning to build a system at 40 gigahertz. So can you modify your code to model 40 gigahertz? Right now, your plot doesn't have 40 gigahertz. I just want to know how much of path loss will be present at 40 gigahertz. So can you model it? Right. So these are the two requirements that came to me. Okay. Okay. The moment these two requirements come, what I do is I take a look at the code. Okay. So I look at the code. Okay. I know that, okay, I've already done the code study. So I know what is meant by the distance variable. I know what is meant by the frequency. And I'm able to go and change that. Okay, another value needs to be added. I'm going to put 8 kilometers here and I'm going to put 40,000. See, it is very important that I don't need to change any other part of the code because everything else is automated, right? I've got an array which is a function of len of d. See, this is very crucial, right? So the moment you put it as len of d, so even though you've increased the array size by 1, right, you don't have to do anything because all your buffer initializations will be automatically happening and you don't have to worry. So this is another very important aspect of coding, which I find is missing in a lot of codes written by freshers, right? That is why I added this point where it is important that you should write a code which is independent of buffer dimensions, meaning you should program it in such a way that if you increase the length of d, automatically things are taken care of. So len of d, and then similarly for your frequency also len of d, and then you have your distance, okay, which is also going to be. So here I put it like that, and I brought up the code. Okay, so frequency, there's a mistake. Is there a mistake that anybody can find out here? There is an issue here in the code. Was anybody able to spot the error? Anybody, can you tell me if there's something wrong with the code? Exactly. Awesome. That's the point. I think for the frequency, I'd made a mistake. Okay, it should actually be FC. np.zeros of FC. Okay, that should actually be the code. And it was very rightly pointed out by Madam. Okay, so let's make the change in the code. Now let's run it. And I have another question here. The question is about what is the constant? Yeah, the constant is right, meaning it is with respect to a minimum of 40 meters. And for that, you have this initial Fresnel distance for which it has been computed as 32.45. Correct. So typically, when you start calculating path loss models, right, if the distance is too less, and when you're taking log values, then it appears that there is path loss is negative, right? So you have to calculate what is called as a Fresnel distance, and then come up with this number which is 32.45. Because even if it is 10 meters, the path loss is always going to be positive, meaning it is not going to be, meaning the receive power is never going to be higher than the transmit power, right? So when you're doing this modeling, you should be careful to understand that even at a distance of 10 or 20 or 30 or 40, you should ensure that there is a basic minimum attenuation, which will be responsible for giving a receive power which is less than transmit power, right? Because your receive power can't be greater than the transmit power. So considering that distance are pretty low in value, and you also have numbers represented in 0.04 and all that, right? The log value will become negative. So you have to figure out what the constant is, and you should automatically put it. And this is coming because of the value like pi and all that in your free space path laws, right? If you look at the free space path laws equation, you will have these factors of pi coming in, and based on that, these numbers have come up. Okay, so that is the answer to. Share the feedback. Which link are they talking about?
Sir, it's the feedback link about the session. It will be shared at the end of the session, sir. So that's what they are asking.
Oh, feedback link. Okay. Fine. Okay. Okay. So that is the background for this. Okay. So I think now we got a hand of what is free space path loss. Now let's go to the next part. Okay, where it's going to be receiver sensitivity and fade margin, right? Typically, wireless communications have this combination of receiver sensitivity and fade margin, where you have your fade margin between 25 to 30 dB, and your receiver sensitivity is going to be defined as the receiver power for which you can have reliable communication. Okay, so the fact is the link adaptation algorithms, right, work on what are called after figuring out the received power and the fading margin, it will work on what are called MCS, what are called modulation and coding schemes, where you will decide whether to transmit a modulation like BPSK with rate half, or you want to go with something like 1024 QAM or 2048 QAM or whatever it is, because your SNR is really good, right? So depending on which side of the spectrum you are, you may want to look at choosing the right MCS, because if you have very good SNR, then you can choose a higher MCS, and you can go for a higher data rate. So that is one of the key ideas of finding out the receiver sensitivity and the appropriate receiver power, because that will in turn affect your choice of MCS index. And based on the MCS index, your data rate on the wireless link is determined. So we will now next quickly look at receiver sensitivity and fade margin and how it typically affects the wireless communication link. Okay, so yeah, that will be the okay. Before that, I think this is also a pretty important slide, where we talk about 4 different bandwidths: 20 megahertz, 40 megahertz, 80 megahertz, and 160 megahertz. And typically, if you look at 20 megahertz, this radius is the range, right? So at 20 megahertz, for this given radius, you can support MCS3, right? So that is the picture that is coming out here. And if you can see at 160 megahertz, right, at the same radius, you can only support something like MCS0. Okay, so this is a very good picture which captures the effect of bandwidth, receiver sensitivity, and MCS index, right? A very good picture that will give you an understanding of what communication can be achieved at what distance based on the channel bandwidth. So, for example, at 160 megahertz channel bandwidth at greater distances from the source, you will find that you can only achieve MCS0. Okay, and similarly, when you look at something like 80 megahertz, right, you can achieve MCS1, where you are achieving MCS0 for 160 megahertz because it is lesser bandwidth, right? So when there is lesser bandwidth, there are 2 aspects. One is your thermal noise power, right, which is a function of your bandwidth, will be lesser, right? And hence your noise floor is lesser. But when you have 160 megahertz and MCS0, you can almost achieve the same rate as 80 megahertz MCS1 because you have more bandwidth. So you need to figure out all these things, right? Which is one of the primary aspects that is done in the industry, right? How will I play around with bandwidth and the typical obstructions which is seen in the field, and how will I come up with numbers on what rate is achieved at certain ranges, right? So this is the sort of graph which are published for products, right? on how is the receiver sensitivity varying with channel width. So this is a pretty useful picture, and I thought I'll introduce you to this before going on to the next simulation, right? So any questions on this? Okay, MCS is modulation encoding scheme. Modulation encoding scheme, where modulation means modulation is BPSK. So I hope that answered Amit's question. If Amit has anything else specific, I think you can unmute and ask. Mr. Amit Birwal. Okay, good. I think now we have gone through the basics of receiver sensitivity, fade margin, and bandwidth with respect to MCS index. So now we are at a good stage to do the next simulation. Okay, so what I'm going to do is I'm going to run the simulation. Before that, let me do a quick code walkthrough. I'm going to be opening wireless link simulation. Okay, so this is going to be my code. So please note that I've initialized the values here. I've got a distance array, which is from 40 meters to 7 kilometers. I'm running simulation for 900 megahertz carrier. The constant is 32.45. Yeah, okay, thanks. So there is a center frequency of 900 megahertz, then the constant, and then you have a transmit power, antenna gain, receive gain, and I'm introducing the SNR of 10 dB, which is typically for BPSK encoded at 1e minus 6 BNR, BER. Okay, and I'm going to put in a variable called receiver sensitivity at minus 80 dBm, and fade margin threshold at 30. Meaning any link which is going to be only above the fading margin, I'm going to accept it. Okay, so that is why I've modeled it this way. And then I'm going to calculate my free space path loss, which is going to be 20 log NP FC, and then 20 log once again D. And then I have a receive power, which is going to be my transmit power plus antenna gain plus receive gain minus PL. Okay, and I compute my fade margin. Okay, where it's going to be a function of receiver power minus receiver sensitivity. Okay, and see, it is important to understand the relationship between fade margin and link availability. Typically, when you're talking about a fade margin of 8 dB, then it is typically 90% available. 18, 99, 28 is 99.9, 38 is 99.99. Okay, and 48 is 98.999. Right. So it is almost like with every gain of 10 dB, right? starting from 18, you start getting 1 9 extra after the dot, right? So it's important to understand this part, because more the fade margin, it's going to definitely impact your simulation, and accordingly you will design it. So it's very important to understand the relationship between fade margin and link availability, and then start your simulation. And of course, once again, there are these two plots here, so distance from transmitter, and then once again the fading threshold margins, which are all given in the code. So if you quickly analyze the code, you will find the initializations are here, right? And then there is a computation here in terms of free space path loss. Then there is a receive power computation, and post the receiver power computation, there is a fade margin computation, and I am plotting the fade margin. Right? So this is the rough code walkthrough. Okay, typically when you start something, you do what is called as a code walkthrough before you start modifying. Okay, so I'm going to run this code now. So is everybody able to see this plot? So this plot, which is based on your free space path loss model, is basically characterizing two things. Okay, on the left side you have the path loss, and on the right side you have the receive power, right? So you can see that when the path loss is very less, right, your receive power is pretty high, right? And for the receive power, you should come here. So you should take this point from this axis. Okay, it's roughly around minus 10 dBm. Okay, and when the path loss increases, right, at 7 kilometers, when you're having such a high path loss, which is going to be here, yeah. So this is your, I'm sorry. So this blue is your path loss. So at 6 kilometers, you're having a path loss of something like 107 dB. Okay, and hence your receive power is something like minus 58, right? So you can clearly see higher the path loss, lesser is the receive power. Okay, so higher the path loss, right, and lesser the receive power. Okay, so here if you see, it is going to be lower the path loss, okay, and hence higher the receive power. Okay, so this is a classical graph, okay, where you understand the interplay between path loss and receive power. Now for this given simulation, now let us see what is the distance at which your fade margin works. Okay, so that is your next plot. Okay, see, this is a very, very important plot. Okay, in this webinar, I would consider that this is the most important plot, because here if you see, right, at a 30 dB margin, and your x-axis represents the distance. So for this given wireless system, you can't have a stable link beyond 2.5 kilometers. Anything in this region, right? Anything in this region is okay. Okay, because you're taking care of the fade margin. Anything here in this region, you can't expect reliable communication. The moment you have the distance between the source and the destination, right? If it crosses 2.5 kilometers, then you are into trouble. That is what this graph depicts. Okay, and see, this is a very, very much sought after graph for a lot of wireless systems. So for wireless systems, given the receiver sensitivity, the path loss, the fade margin, if this graph is drawn, then you get an idea of what is the range that the wireless system can support, right? So this is a very, very important plot, and I would request you to ask any doubts or questions at this point in time, because this I would say is one of the most important takeaways of today's webinar. Okay, because you can now change the simulation for different frequencies, distances, and whatnot, and keep computing this for different requirements. Okay, so any questions on this?
Hello.
Yeah,
So I have a question here.
please.
This red line shows 20 fade margin value 20. Can you show the graph again?
It is 30.
30 red line.
Correct.
Yeah, but you mentioned like even if the fade margin is 8, so 90% of link available.
Correct.
So how you can say like link is unavailable below this line?
Exactly. See, the point here is depending on your environment, right, and the amount of fade margin that you can allow, you would want to play around with the fade margin. Okay, so let us assume you're okay with certain amount of unreliable communication, and you're okay with 90% of reliability. Then you can go ahead, change the simulation. In the simulation, right, you can change your so this variable. This is 30, right? You're able to see the screen. Hello.
Yes, I can see.
Yeah. So you can change this variable depending on what you think is your particular wireless system that you're designing, and then with that degree of reliability, you can go ahead and design. See, this is left as an option to the wireless designer. I am
Okay.
claiming that with 8 dB fading margin, the link is only 90% available. That means it is not available for 10% of the time. If you're okay with that, you can go ahead and design.
Okay.
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 This is a parameter given to the wireless designer and to come up with his own design. I am choosing it to be 30 dB because I want to be here. If you look at that, right, there is a direct connection. See, if you look at this table, right, so 28 is 99.9.
Okay. So what is the typical value for wireless routers or access points that we used?
See, that's what. There also it varies depending on the product, right? So today we'll be looking at a product called Zyxel. Okay. There are routers which are meant for enterprise applications. There are routers meant for home type applications, right? So depending on what you want to do, right? And there are even routers meant for rural areas where across one point and another point, right? There could be large amount of LOS components. Okay. So depending on the environment and depending on your applications, the fade margin would vary. But typically for a multipath delay profile, right, between 25 and 30 dB is considered as your link margin for a typical multipath scenario. Where if you categorize your RMS delay spread and you look at your typical channel characteristics, right? For that,
So
typical wireless link, you can look at 25 to 30 dB.
this will include this fading loss that we have multipath propagation.
See, typically what happens is you model for LOS and then you add a fading margin for multipath.
Okay.
Okay, you see typical communications either LOS or NLOS, right? Line of sight or non-line of sight. Okay,
Yes.
so you model the line of sight component using a free space path loss and add a fading margin based on your multipath. Because any signal, even if you work it out for LOS, right, there would be a tree, there will be some obstacle, even in rural areas, because of which it become NLOS, right? Even in the best of conditions, there will be NLOS sort of reflections. And for that, you model this extra parameter and you come up with it. Okay. So, is that fine?
Yes. Yes. Thank you.
Sure. Okay, I think Dr. Saurabh Jain has a question. He was talking, he's saying differentiate between DB, DBM, and DBI. So quickly saying DB is a measure of, it's a measure of loss or gain. DBM is the unit of power. So for example, it could, when you talk about DBM, right, you're basically talking about milliwatt in linear scale getting converted into DBM in log scale. And when you're talking about DBI, you're talking about, once again, a dimensionless quantity, but with respect to an isotropic catena. And that is what is DBI. Okay, so DB is, DB or DBI is basically gain or loss. Okay, DBM is absolute power. So when you have a milliwatt getting converted into a log scale, it is dBm. And dBi, which is a dimensionless quantity, is with respect to a isotropic antenna, right? So I hope that answers this question, Dr. Saurabh Jain. Sure. Okay, so let's move ahead. We have a lot of things to cover, so I think let me start rushing up. So I think I leave this exercise to the viewers, right? In the sense, we are primarily talking about this wireless link simulation, where what I'm now going to do is you can change around and play around with it now that you have an idea about how the code works and all that, right? So, for example, requirement 1, which is minus 85 dBm and 20 dB, okay, you need to basically go and plug it here. So I'm going to plug it here and play around with it. Okay, but be careful. You have to think about all aspects of the code. Primarily your fixed point issues, the precision issues. You have to think about it and modify the code. Okay, and please try it out and get back to me if you have any issues. You can write to me at my email ID, and we'll see how to work it out. But the crucial part here is that you must have an understanding of precision effects, right? So for that, I've given you these requirements. Okay, minus 85 dBm and a fade margin threshold of 20 dB, and then another minus receiver sensitivity. Sorry, receiver sensitivity is going to be changed here. I made a mistake. Receiver sensitivity is going to be changed in this part. This is where you will change it. Okay, and you will come up with new numbers. So maybe let's just quickly run it for one. Okay, so what is the requirement? Requirement is minus 85 and 20. So I'm going to make it minus 85 and I make this 20. Okay, and I'm saving it. So this is the new model that I'm getting. This is for your minus 85 and 20 dB fade margin. And here you can see this communication system comfortably works for 7 kilometers. So now what should I do next? Now I'm going to show this to my customer. He's saying, okay, for this requirement, I've got this plot. What will be the next natural question if I show him this plot? Is everybody able to see the plot? See, the red line is not interfering with the blue line at all. So what is the inference? Anybody, can you tell me what is the inference on seeing this plot? Transmit less power. Exactly. Design works well. Excellent. See, this is the crucial point. Okay. The other thing is, as all of you have pointed out, right? You can either transmit less power or I can increase the distance, right? So I can now make the same system work maybe for a slightly more greater distance. I do not limit it to only 7 kilometers, right? I can afford to go a bit more and see if I can get more points in my graph, because my receiver system now works for a larger distance, right? Which is good because my range is increased. Fine. So, and what did I change? I changed my I changed the receiver sensitivity and I reduced my threshold, right? I think that is also something which he was asking before. So I'm willing enough to work, live with a 99% availability, right? If that is what is your design constraint, right, then your range increases, right? So let us do it once again. I'm going to do minus 90 and 15 now. So I'm going to do requirement 2, which is minus 90 dBm and 15. I'm going to do minus 90 and 15 here. So this is the path loss. This proves the point, right? So now I can reduce the transmit power or increase the range, right? On doing this. So you can potentially try the other side also. I came this side and showed you what is happening to the link margin and whatnot by reducing it. You can increase the link margin. You can also play around with the transmit power, and you can get to understand a lot of things on when is the link becoming unavailable, right? A few simple plots by which you can find out what is happening. And since I put here 15, it is showing here as 15, right? So that illustrates the point. Okay. So any questions on this? Any questions or any comments, or shall we go on to the next step? I think I'll go forward. Okay. So now comes the fairly important part of the webinar, where we are going to now analyze a product. Okay. So this product is a 11AX AP. Okay. So this is the product that we are going to be looking at. So this is an 802.11AX. Okay. It's a dual radio unified pro access point. Okay. And I'm primarily interested in looking at its RF performance. Okay. So I want to know what are the data given in the data sheet as far as its RF performance is concerned. So I'm just going through that. Okay. So typically these days, all your Wi-Fi access points are having BLE beacon integrated and IoT ready. Okay. So this is for your location assistance, where they have integrated BLE technology with your Wi-Fi access points. And of course, 11AX has a very different perspective, in the sense they want to increase the density, meaning these access points are meant for places of high density, and how you could potentially work on those areas. So that is the objective of 11AX. And for that, they have designed this AP. And what is interesting is, see, when you talk about the hardware design, right, they're talking about 3 layers. One is the heat spreader, the other one is the smart antenna design, and the third is the scanning radio. Okay. So typically these hardware designs come across as 3 different layers, and the functionalities are pretty different. And from an RF point of view, you're more interested in things like scanning radio and smart antenna design, and that is what we'll be looking at from. Okay. And once again, this AP can be used in 3 modes. One is as an on-premise controller. It could be a standalone AP, or it could be a part of your control center. Okay, it could switch across 3 modes. Okay, and let us look at the requirements that we have. Okay, so the product name is 11AX Pro Access Point. Standard is, it supports everything. See, the 802.11 standards, right? From AX to A, it supports everything. So this is a crucial point. Now it says it supports multi-user MIMO, and at 2.4 gigahertz it gives around close to 1 Gbps, and at 5 gigahertz it claims it gives around 2.5 Gbps. Okay, and frequency band is 2.4. It has these frequencies, and Europe it has these frequencies, and you can look at all these aspects. Now my point of interest is these things. Okay. 28 dBm, 19/26, okay, and then it has a 4x4 smart antenna, and a peak gain of 3 dBi in 2.4 gigahertz, a peak gain of 5.8 dBi in 5 gigahertz, and the receiver sensitivity is -105. Okay, so what I would request the participants would be to take these numbers, plug it into those models, and try it out, and let me know the results. Right, meaning you can do it sometime in the next day or 2, where you can potentially look at this product, okay, try to run it in that code and see the sort of result you're coming. Because see, it is very important to run the simulation models on a product that is developed, so you will get to understand more about the product, right? Because you've taken this, you have an idea of what is meant by free space path loss, then you plug in these numbers and see the rate and the range, meaning the range at which it starts failing. Meaning you can assume your fading margin to be 20 dB or 30 dB or 40 dB or whatever it is, and you can find out at what distance it starts failing. Meaning for a given link availability, you can use these numbers and do it. Okay, and as a part of it, I think you may also want to look at the other features that it offers. For example, there is something called band steering. There is WDS, which is wireless distribution systems. Then there's a mesh AP, right? So typically these days, all APs are coming as what are called self-organized networks. Okay, so when you talk about self-organized networks, right, you're talking about typically self-configuration, self-healing, self-defending without a necessary need to reconfigure, right? The AP itself should be able to figure out the changes in the environment, meaning with respect to transmit power or interference, or let us assume even a DOS attack. If there is a security attack, it should be able to reconfigure its settings and it should start working. So that is where your concept of smart mesh is coming. And of course, fast roaming. So typically when you have, say, a couple of APs in a typical establishment, right? Considering that the users who are going to be in the ground floor and the first floor are both authorized, they should not be, they should not take too long a time to get associated with the other AP. So in which case you do what is called as fast roaming. And then you have what is called dynamic channel selection, load balancing. So see, there are multiple features here in a typical product, right? And I believe that when you have an understanding of all these features, right, which is WLAN features, security, and of course networking, okay, how does it work with an IP network, right? And typically, how are you going to manage it, right? See, let us assume you want to do certain sort of centralized batch configurations. Do you have a web GUI access? What is the strategy for firmware upgrade? All those will come as part of your management, right? And then your configurations, your typical RF planning, your coverage detection, all that will come as part of your management. And finally, your physical specifications, meaning your box, meaning what is the dimensions, W cross D cross H, and the weight, and typically the other accessories which are included, right? Your mounting plate and screws and whatnot. And see, this is another, once again, a very important parameter, your MTBF, which is your mean time between failures, right? He's saying it's around 1,80,000 hours for your average failure. Okay, that is also a very important parameter that I look at before deciding on the quality of the AP. And then you have external interfaces, meaning the form of for Ethernet and for power, and the operating conditions, meaning can it work between certain temperatures and whatnot, the humidity, temperature, storage, and all that. And finally, the certifications. In the certifications, you typically have radio, EMC, and safety standards. Okay, so this is a typical product. Okay, and from an RF point of view, what is of interest is going to be things like receiver sensitivity, which is minus 105. Okay, which is given here. Then the transmit power. The transmit power varies between 2.4 and 5 gigahertz in a European based system, and the bandwidths. See, you have 4 different bandwidths in WLAN, which is at 20, 40, 80, 160, and you may want to look at all these options and include this in your model and see the performance. See, for example, you can typically do the same WLAN performance for this. Okay, so let us quickly do that. Okay, I'm going to do this 2828. So any questions on this product brief? I hope people got the idea about what we are doing now.
Hello.
Yeah, Amit.
I have one question regarding transmit power.
Yeah.
It is mentioned for US and Europe. What about India?
Okay. I just need to check that part. I think even in India it comes under FCC. That part I need to check.
Okay.
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 See, you have 2 standards, right? FCC and HC. Okay. So based on what is the band, meaning standard followed, we may look at that and come up with an answer.
Okay. Thank you.
Yeah. Anything else? we just saw the product brief, and if anybody has any questions or anything which needs to be clarified, you can post it or ask. Okay, maybe we'll just quickly simulate it. We'll see the effect of it and see what happens. So I'm going to go back to this. Okay, I'm going to program it as 2400 megahertz. Okay, constant is going to be the same. Transmit power is going to be 28, and this is going to be I'm going to put it as 3 dBi. Receiver sensitivity, I'm going to put it as minus 105. I'm going to put a link of 30 dB margin, and I'm going to run it. So what I've done is I've taken all the parameters from the data sheet and I'm running my model now, where I've made it 28, 3 dB antenna gains, SNR I'm going to continue to have it as 10, receiver sensitivity is minus 105, and fade margin is 30. Okay, so I'm going to run it now. Okay. So what is the interpretation now for Zyxel? At what distance from the transmitter am I going to start losing communication with a 30 dB link? Any answers? Exactly. It's going to be around 2.9 kilometers where I'm going to start. And so, so can anybody tell me what MCS I can say support at around 2.7 kilometers, 2.7 or 2.6 kilometers? What MCS can I support? At a distance of say 2.6 or 2.7 kilometers, what MCS can I support? If it is going to be a 30 dB fading margin. Exactly. So it will be BPSK, which is like something like MCS 0, where you can do a BPSK of rate half, will be the answer. BPSK rate 1/2 is something which we can afford to do it at something like say 2.6 kilometers or something, where it is almost going to stop working. So now let us run the same simulation with a 20 dB fading margin. Let's see what happens. So you take the code, you run it at 20 dB fading margin and run the same code again. Okay, so once again you get your free space path loss. So now what happens the moment you do 20 dB, okay, once again we are hitting the same situation as we did before, right? We can either transmit lesser power or we can increase the range, right? So all these options come for you because we are willing enough to work with the link reliability of 90%. Okay, so that is the plot that you're getting now, where I've changed it from 30 dB to 20 dB as your fading margin. Okay, so see, this is a very typical study that is done to find out how well your routers perform. Okay, so any questions on this? Any questions or any clarifications? Okay, so fine. I think I'll move forward. So that gives you a perspective of an actual product. See, for example, we looked at this product, we analyzed it, and we picked up numbers from this, and we tried to use it in our simulation and try to find out at what distances you can have communication, and we came up with those parts. right? So let us move forward. Okay, so you can do these things. So for example, you can modify the wireless link SIMU3 as per the product brief given for UU 2.4 gigahertz. You can also do it for UU 5 gigahertz, and you can see the performance. Especially when you start putting at 5 gigahertz, you have to remember that larger the frequency, it's going to be greater path loss. So you'll see shifts in all these things because your range will obviously come down. But I would request you to try all those things and form an idea for yourself. The effect of frequency, the effect of path loss, and you have a certain picture. Okay, so now we are all set for the next stage, which is going to be, okay, now we know what is meant by receiver sensitivity, but can we model it, right? So that is a very important aspect, right? In the sense, how will you write a code now given a new requirement? So simulation 4 is about writing our own code and trying to find out how it works. So I've given all the specifications here, okay, about the SNR being 10 dB, the noise figure being 15 dB, the bandwidth being 20 megahertz, the Boltzmann's constant is 1.38 into 10 power minus 3 joules per Kelvin, the temperature is 290 Kelvin, and then the formula to compute the receiver sensitivity is going to be thermal noise power plus noise figure and SNR. Okay, so this is how your receiver sensitivity is computed. So for people who don't know what is meant by noise figure is part of your LNA or the first stage amplifier in a typical receiver system. And typically, since it's an amplifier, it will also amplify your signal as well as noise. So unless and until you have a pretty good noise figure, your noise will also get amplified, right? So it is important to have your noise figures as less as possible. Lower the noise figure, the better the meaning the lesser is the noise amplification, right? Which means the further stages of amplifiers, right, will see lesser noise. So one of the most important ideas in order to figure out your receiver sensitivity is to have lower noise figures, and there is a big amount of research that happens there. Meaning when it comes to a front-end amplifier design, right, or your first stage amplifier, the reduction of noise figure is a big area of research where a lot of work is happening. And next comes is your SNR. Okay, so your receiver sensitivity can either be improved by looking at reducing your noise figure or by looking at the SNR without compromising on your BER, right? See, because reducing your SNR is fine, but that should happen without compromising your BER. And then you come up with lower RX sensitivity. Because see, thermal noise power is fixed for a given temperature and a bandwidth, right? There is nothing that you can do because it is about motion of electrons. So there is really nothing that can be done when it comes to thermal noise power. So receiver sensitivity, which is a component, which is a combination of three things, which is thermal noise power, noise figure, and SNR. We can only look at potentially working out with noise factor, noise figure, and SNR. Okay, so I'm not going to do the coding, so I can quickly show you how the code looks like. Okay. So the code is basically going to look like this. Okay, you have bandwidth which is 20 megahertz. You have a Boltzmann constant which is 1.3 and 10 power minus 23. Then you have a temperature 290 Kelvin, RX NF, which is a noise figure. I'm going to put it as 15. Then SNR is 10, and then I compute the thermal noise power, which is 10 log NP K into temperature into bandwidth. Then thermal noise power, then I compute the receiver sensitivity, right? So this is roughly what is the coding. So maybe you can code this and change the bandwidth here as 40 megahertz, 80 megahertz, 160 megahertz. So can anybody tell me what will happen? Meaning when you start increasing the bandwidth, what will happen to the receiver sensitivity? Will it increase or decrease? Any idea on what will happen to the receiver sensitivity when you increase the bandwidth? So you compute the receiver sensitivity with say 20 megahertz, and you get the value as say minus 100 dBm. And when you make it 40 megahertz, what will happen? The receiver sensitivity will Meaning, so if it is minus 100, will it become minus 110 or will it become minus 90? Right. So that means what is the inference? At higher bandwidths, I'm going to have a receiver sensitivity of minus 90. Is it good for a wireless link or not? Can I afford higher MCS there? What is the next inference? So you have a 20 megahertz at minus 100 dBm and 40 megahertz at minus 90. So in which link can I transmit more data? Okay, it is good. Okay. But you've now just seen, right? If you have a fade margin of 30 dB, which will it be 20 megahertz or 40 megahertz, which will give you a greater range? Range wise, can someone tell me an answer with respect to range? Mm-hmm. So which bandwidth configuration? Is it 20 megahertz or 40 megahertz that will give me greater range? Because 40 megahertz means more thermal noise power, right? Awesome. This is a standard thing which happens. So so you could analyze all that. See, the point is that I think you can plug in these numbers, vary the receiver sensitivity, and try to understand you can run the other graph, the third simulation, right? And come up with numbers. Okay. But I think the answer is 20 megahertz. The answer will be 20 megahertz because your receiver sensitivity would be higher, meaning it will be at minus 100 dBm. And hence your fade margins can work. It will still continue to be at 30 dB and you will be able to come up with a greater range, right? So you'll have to be able to analyze all these things. This is why we build simulation models, right? So you can vary these numbers, you can plug these numbers and try to come up with, okay. So let us just do that simulation quickly. So here, yeah, you have bandwidth of this and you come up with the numbers. You can maybe write a similar code and you can figure it out. It should be pretty easy. Okay. So it is just a few initializations and whatnot, and you must be able to do it. Okay. So that gets us to the end of receiver sensitivity. Okay. Another very, very important topic when it comes to RF for wireless communications, right? So any questions on this? Okay. If there are any questions, you can post it, but I'll move forward in because we need to save time. So the next aspect that I'm going to be looking at is how do I improve receiver sensitivity? So typically there are two ways. One is to look at reducing the noise figure at the front of the end of the amplifier, and the reduce SNR without compromising on the BER requirement. Okay, and how can I achieve that? Is going to be by it's typically when you talk about an LNA design, right? There are device level variables and there are board level variables, right? That is, this is where circuit designers play a pretty big role. When you want to reduce noise figure so that you can come up with improved receiver sensitivity, which is like, when I say improved receiver sensitivity, I mean going from minus 105 dBm for 20 megahertz to minus 110 dBm for 20 megahertz. That is what I mean by improved receiver sensitivity, because that will enable me to improve my range, right, for a given fading margin. So how do I do that? Is by two factors. One is the noise figure and the other one is your improving the SNR. So the noise figure is improved by two actions. One is the device level, like process technology, circuit topology, package parasitics, transistor geometry. See, these are where the device people come into the picture. The other one is the board level variables, meaning layout and grounding, EMI shielding, output or input matching, and supply decoupling. So these are standard techniques which people working on the PCB areas and working on process technology would be aware of. And the surprising part is when you take up the FSPL, the free space path loss improvement, right? You will figure out that for a 0.2 dB improvement in NF, right? So for example, if it becomes from 10 to 9.8, there's a 2.3% improvement in range. Similarly, if it comes from 10 to 1, which is a 1 dB improvement, there is 11% improvement in range, right? So these are pretty strong numbers, right? In the sense, the amount of variation that it can bring up when you vary your noise figure with respect to FSPL. These are pretty good numbers to look at and see if your simulation is really giving you these numbers. Meaning these are coming up with another LNA design from Freescale. Meaning we are doing some analysis for, meaning we used to do some analysis for a company called Freescale before, where these numbers came up, and I'm just quoting it here. But this is the power of working around with noise figures, right? The next part is improving SNR, okay? Where typically when you talk about improving SNR, you have time diversity, frequency diversity, and space diversity. Where when you talk about time diversity, you're talking about coding and interleaving. When you're talking about frequency diversity, you're not actually sending the same information in two different tones, but spreading the information across multiple tones, which is your frequency diversity. And of course, your space diversity, where you have your TX and RX diversity, where you have one TX and multiple RX, or multiple TX and one RX, right? So these are typical ways by which, without increasing the transmit power, but you achieve better reliability of communication by one of these techniques. So these are prime and tried techniques. So here, what I would want to do is show you a performance improvement for one case in space diversity. See, for example, this is one really good plot where the yellow corresponds to your BPSK for Raleigh, which is uncoded. So you can typically see for 1E minus 3, right? You have something close to 24 dB. Okay, 1E minus 3, you have around 24 dB for a 1TX 1RX case. Whereas for the same 1E minus 3, you're operating at something like 11 dB. So there's a 13 dB gain for a BPSK modulation scheme when you have multiple antennas, right? So this is the power of space diversity when you use multiple antennas for improving SNR. Okay, and the moment you improve SNR, your receiver sensitivity is going to go down. Meaning, from minus 105 it will go to minus 110, which means it will improve your range, right? So this is how wireless communication is interlinked, right? When you talk about device, when you talk about multiple antenna communication and SNR, this is the sort of results that you should be looking at to connect the improvement in SNR with your space diversity. Okay, so you can clearly see here these two graphs are representing your 1TX 2RX and 2TX 1RX. Okay, which is 2TX 1RX is your beamforming on your TX, and 1TX 2RX is your maximal ratio combining at the receiver. And when you look at this graph, where you have your uncoded BPSK for 1TX 1RX, which is yellow, and blue is 2TX 1RX without no beamforming. You don't find any difference at all. But when you take a typical 1E minus 3 point, the difference is close to 14 dB. This is 11 and this is around 24, which is around 13 dB. And that is how you can improve SNR. So we quickly saw two ways by which you can potentially improve your receiver sensitivity. One is by reducing the noise figure. The other one is by improving the SNR, which is, once again, we are going to reduce the SNR. What is 10 dB needed? I'm going to reduce it. And how can I reduce it? Is by using either multi-antenna communications or time diversity or frequency diversity. Here, with respect to multi-antenna communication, we saw both transmit beamforming and receive beamforming, where you call 2TX 1RX as transmit beamforming and 1TX 2RX as receiver beamforming, and we saw the results here. Okay, so we can clearly note that there's a significant advantage of around 13 dB between the two cases, right? So that is the two ways by which you can improve your receiver sensitivity. Any questions on this? Yeah. See, madam has asked about. See, what I want to do is the receiver sensitivity equation, right? If you look at the equation. So, madam has asked about, see, the receiver sensitivity is a summation of noise floor plus SNR plus noise figure. So, when I talk about receiver sensitivity, I'm talking about noise floor plus SNR plus noise figure. Okay. If I want to reduce my receiver sensitivity, right, if it is minus 105, it has to go down to minus 110, because at minus 110, I'll get a greater range. Then I'll have to reduce my SNR and reduce my noise figure without affecting my BER. Right, the BER should continue, meaning if my BER requirement is 1 in 10 power minus 6, right, then I should ensure that even at reduced SNRs, I should get 1 e minus 6, right? So in that case, I'll look at other ways, meaning either I'll go in for certain amount of coding and interleaving in time diversity, or I'll look at multi-antenna communication. So like that, I'll try to improve SNR, where I'll try to achieve the same BER at a lower SNR. Okay, so it is to no, I'm just typing for everybody's benefit. So I hope the point is clear. If I can make my if I can make the receiver sensitivity go to minus 105 dB, minus 110 dBm by lowering SNR and still not compromising on my BER, right? My range increases, right? So my aim is to ensure that if I can work with a receiver sensitivity of minus 110 dBm, then I would want to work on other techniques like MIMO or coding and interleaving, and trying to bring up that. Okay, so I hope that clarified the point. Okay, fine. So I think now we saw two techniques by which we can reduce the receiver sensitivity, and with that, I'm going to go into a section called the wireless deployment. Okay, so here we are now going to discuss a case study of a typical deployment on how Wi-Fi is being used, and we will quickly look at some insights from the deployment scenario. Right. See, now that you have certain background on the different aspects of RF, right, it is a good time to look at deployment and look at what is happening there. So, for example, here you can see A is your access point, and B, C, D are your clients. Okay, in B, somebody is talking on the phone. C, somebody is listening to a radio on Wi-Fi, and somebody is using their laptops. So, typically, this is a deployment in a home, right? So, you have people in separate rooms. That is separated by walls. There are metal cabinets. Then there are signal transmission losses. This is a typical deployment scenario where you have one AP which is transmitting and different clients in different parts. Okay, so A is the access point of the device connected to the internet cloud through an ISP. It provides wireless connectivity to clients, and B, C, D are the clients that get connected to the AP. So A is actually connected to the internet cloud. So that is how the architecture is. So typical home profiles in developed nations, if you look at it, right, you have 2 APs, 12 to 15 clients, and demanding these applications. Typically, OTT platforms like Netflix, you have gaming consoles, then IP audio and video, which is real time, because right now what we are doing is real time, right? So typically going across an IP network. Then you have YouTube videos, then you have wireless doorbells, because if somebody has come to your house and you want to give them access, right? Now that typically is over a WLAN network, where the photograph of the person who is standing outside the door is coming on a wireless network to you on your phone. Then you find out whether he is somebody known to you and then give him access. And similarly, there's a wireless security camera outside the house. There's a wireless camera inside the house for pet or baby monitoring. So this is typically the applications which are being used in a house like this. Okay, you have a house and you have so many APs and so many clients going around with these sort of applications. Okay, and some are real time, some are non-real time. So based on that, you will have varying performance requirements. Now let us take a quick look on what is the data rate. Okay, so when you talk about audio calls, typically on downlink and uplink, you need around 50 kbps. For video calls with screen sharing, you typically require around 200 kbps. For high definition video, it is around 1.5 mbps. And you have video plus a 5 group call, and everybody is on video, you require around 3 mbps slash 300 kbps. So these are typical numbers which your application demands. And then when you talk about over the top, right, meaning on top of, meaning your Netflix and things like that, when you have streaming, you have 3 mbps and 5 mbps as a requirement. And the highest requirement comes for gaming. Okay, depending on whether it is a 720 point or a 4K, the requirements are going to be 10 mbps or 35 mbps. So this is the rough application level profiling on what is being used today in typical context, where it's a combination of audio video calls, and then you have over the top content coming from Netflix and whatnot, and gaming. Okay, and these are some of the most demanding applications. Okay, so given this sort of a scenario deployment, and then you have these typical number of APs and clients, what are the insights from Wi-Fi deployments? See, now given such a deployment, right, what is happening? Okay, when you talk about people looking at deployment situations, right? So it is very important when you're going and doing a certain amount of deployment to take into consideration the wall thickness, the metallic cabinets and doors, because they all contribute very significantly to the propagation loss that we're talking about. The free space path loss that we modeled doesn't talk about that. Okay, so similarly, the humidity content in the air, and then a very, very significant thing whenever you're deploying for rural-based wireless systems, right? If you want line of sight, the cable losses, right? Because when you're connecting your base station, meaning your module with the antenna, if you're going to use a lot of cables, then the losses on the cables are pretty high. Okay, so even though it is better to place the antenna at a higher, meaning higher the antenna the better, because for better LOS, you should also consider your cable losses, because the cable losses will take a lot of your energy and it can ruin your link budget. So another thing to be worried about is your RF cable losses when you're setting up, when you're deploying. Then there are features like AP steering, where the AP will work between 2.4 gigahertz and 5 gigahertz based on the number of clients attached to it. See, for example, if 2.4 gigahertz band is overloaded, it moves to 5 gigahertz. If 5 gigahertz is overloaded, it moves to 2.4 gigahertz. Like that, it does what is called as AP steering or load balancing and tries to work between these two bands. And another very important aspect is typically people who are more closer to the AP, they are given a band in 5 gigahertz, and user equipments which are away from the AP are given bands in 2.4 gigahertz, because you understand that 2.4 gigahertz can serve people at a longer distance. So all these state machines are running within AP, right? So you have all these things happening, and if there is an issue in the code, right, then you will find strange things happening in the deployment scenarios, because if the state machine, if there is an issue and it was not being tested, right, then you will find that AP steering is not happening properly, right? Load balancing is not happening properly. So you will notice all these insights from field deployments. Similarly, another very interesting thing is, let us assume you're watching YouTube video and you're walking out from your house and going to the street. So it will mean that when you're closer to the base AP, you'll be at 5 gigahertz. Then you'll move to 2.4 gigahertz. And then the moment you go outside, you'll go to cellular. And then when you start coming back, you'll come from cellular to 2.4 and then from 2.4 to 5G, right? So this is the typical switching happens, there are issues in these things when you're looking at typical Wi-Fi deployments. So we need to be aware of all this. And then, of course, since we are using an unlicensed band, right, there could be heavy amount of interference. The interference is in the form of Bluetooth, cordless phones, microwave ovens, and if you're talking about 5 gigahertz, there is radar. So all these interference issues you should be aware of, right? And then security considerations. See, considering that this is going to be WLAN and it's an unlicensed band, right? Security is a big concern. And all customers want it as cost is a very important factor, meaning there should be low cost and low maintenance, right? So we need to work on this. And of course, firmware updates. Over-the-air firmware updates is a very integral part, meaning your code design should be ready for taking up over-the-air firmware updates. And for that, you should design the code accordingly. And of course, meaning self-organized networks, so that minimal reconfiguration is required when products adapt based on changing environment, because a wireless environment is going to be constantly changing, right? So there could be high level of noise, there could be high level of interference because somebody else has started their AP. So the necessity for these products to be self-organizing, right, is extremely important. So these are the insights that you get from Wi-Fi field deployments, and you would want to see if you have configured your Wi-Fi properly, so that you get the maximum performance, right? And these are typically that we are observing as issues in the field also, right? So what we saw was a typical deployment scenario where this is the typical traffic profiling, where you have 2 APs and 12 to 15 clients. And then what is the data rate required for IP calling, then streaming and gaming. And for that, where are the issues when it comes to RF, when it comes to software, when it comes to interference, and of course, security and cost and maintenance. These are some insights from Wi-Fi deployments, right? So this is what I wanted to cover, in the sense, start with some basics of RF and then do some simulations, then look at a product, understand certain aspects of the product, draw the graphs for it, and then talk about a real life deployment, and give you some insights on how deployment issues are being handled. Okay, so this is roughly where we are heading, meaning we have 4 simulations, we have done 4 simulations, large code bases. Any question before that, before I go to the conclusion? Any questions from anybody? Okay, what is the best algorithm present current? So first let me thank. Okay, so when you're talking about algorithms, right? There are okay, so I have got a few questions here. Let me maybe take it. Best algorithm presently. Okay, see, in 5G technology, see, there are these optimizations which are happening at the scheduler level. See, 5G has so many options in your hand. There are a lot of interesting machine learning based schedulers which are coming up on the algorithm part as far as 5G technology is concerned. And depending on that, there are going to be pretty good algorithms. And in fact, even convex optimization is being used as far as 5G is concerned in order to come up with good algorithm. I can't name one particular algorithm, but I can tell you the mechanisms which are right now being used in the 5G schedulers to optimize. For example, there is bitrate to be optimized, the bandwidth, the number of antennas, then your modulation encoding scheme. End-to-end optimization is right now happening for 5G, where the schedulers are using very fairly advanced algorithms, right? Once again, minimum and maximum data rate of 5G communication, lower band and high band. Obviously, when it comes to lower band, considering your path losses are going to be reduced, so you will have, meaning everybody wants to work on the lower band, right? So because there is much lesser path loss and much greater incentive to build it. But once again, when you go to higher band, since there are large amount of bandwidths available, you can come up with a completely different set of numbers. I don't have exact numbers, sir. I'm sorry, Mr. Rakesh. I don't have exact numbers with me, but I can tell you what is happening at the lower band and higher band. The sense that the different two types of medium are such that since you have higher bandwidth in the higher band, meaning at 60 gigahertz and whatnot, if you can work out all these noise figure related stuff, you can go and achieve fairly decent rates. But the range would be pretty limited, and that is how you should consider. The exact numbers I will have to check up and get back to you. Okay, so just one quick, I'll maybe just wrap it up with the conclusion then. Okay, so the conclusion is that what we looked at 4 simulations. Large code bases are already available. Okay, development testing is requirement based and is referred to as a change request or a feature request. This is how we typically get it from our customers. Understanding the current code base is very important, and that's what we did today. We did a quick code walkthrough, and we try to figure out what is happening. And interpreting results through plots and graphs is also very important. Solving field issues by doing log analysis is our bread and butter. That is where we do a lot of work, primarily on Wireshark and using Python and whatnot and all that. So for aspects related to anything on 5G or WLAN research, right, we are specializing on the embedded systems part of it. Okay. And anybody who wants any questions to be answered, any queries or any collaborative approach or whatnot, feel free to write at ashok@zilogic.com. You can maybe paste it on. We do a lot of work on from an embedded systems point of view, where we look at typical architectures and build it. Even we have so that is roughly my session. I hope it was useful, and I didn't want to also cross the time. It is already 1 o'clock. Everybody might be hungry, so I don't want to really stop you from your lunch. But you've actually been an awesome audience, in spite of the fact that this is a webinar, right? I have got a lot of questions, and I'm very happy to have been of use to you people, that I was able to share this session. So once again, I think I'll thank the HOD, Mr. Suresh Babu, Madam Geeta Priya, Madam Ramesh, and all the other people involved in this setting up. Thanks a lot.
Sir?
Yes, Ramesh, you can take over.
Yes, sir. We are seeing the chat box with full of informative session and very good session, like that kind of messages we are able to see. And one more thing, I wanted to share that we have almost around 90 plus participants who are there from 10:30 to 1 o'clock. They didn't leave the session at all. The other webinars we conducted, actually the people come in and go, but in this we are able to see all the people that still in the session for the long time, and we are very much delighted to have a resource person like you, sir. And thank you very much, sir.
Sure, sir. I'm so happy. I'm so happy to know that.
Yes, sir. And before going for vote of thanks, we have some information to the participants, sir. Can I proceed with that, sir?
Please. I'll mute it.
Yes, sir. Yes, sir. And information to the participants, I have shared the feedback link And please try to fill the feedback form before 1:30 p.m. in order to get your e-certificates. And don't forget to fill your e-certificates. I'll share the link of feedback also. And before going into vote of thanks, is there any participants who are going to have oral feedback session? Any participants who are going to have oral feedback session? If not, thank you one and all. I request our coordinator, Engineer Jayalakshmi ma'am, to give the vote of thanks.
Sir, first of all, I thank Lord Almighty for making this webinar on RF fundamentals for wireless communications organized by Kamaraj College of Engineering and Technology. I thank our resource person, Mr. Ashok Govindarajan, Head Wireless Networks, Zilogic Systems, for accepting our invitation, though he is in tight schedule. Thank you, sir. I thank our management, principal, and head of the department for their support in arranging this webinar. I thank our department faculty members, Ramesh sir and Alvin sir, who worked with us for the successful conduct of this meeting. Finally, I thank all the participants who have attended this session sincerely and get benefited. Thank you, one and all.